Welcome to the Chemistry 450 Atomic and Molecular Clusters video series. In this video, I will discuss potential energy surface mapping. The potential energy surface of a molecule is defined by the Coulombic attraction between electrons and nuclei and the repulsions between similarly charged particles. By invoking the Born-Oppenheimer approximation, one is able to solve the electronic Schrödinger equation parametrically as a function of nuclear geometry to create an electronic potential energy surface in nuclear configuration space. If we calculate the electronic energies for cluster fragments of bulk crystals, we find that structures which exhibit higher atomic coordination numbers are favored. However, this begs the question, are bulk crystal fragments optimal cluster geometries? We can answer this question by exploring the potential energy surface. Stable nuclear configurations occur at local minima on molecular potential energy surfaces. These are locations where the gradient of the surface is zero and the forces acting on the nuclei vanish. One can find these stationary points by searching for configurations of nuclei where the first derivative of the potential is zero and the second derivative is positive. A negative second derivative is indicative of a local maximum in the associated coordinate. This occurs for transition states and higher order saddle points. If we apply geometry optimization via gradient descent to our sodium-8 crystal lattice fragments, we find that optimal geometries are significantly distorted from bulk crystal structures. For example, the cubic isomer contracts upon optimization such that the cluster volume halves and the density doubles. Interestingly, the lowest energy isomer of sodium-8 turns out to be a bicapped boat structure that is based on a polytetrahedral growth mechanism. Such a crystal growth mechanism would yield a face-centered cubic crystal lattice and not the body-centered cubic structure of bulk sodium. This underscores two important considerations in cluster science. First, the structures and properties of clusters are not necessarily similar to those of the bulk condensed phase. And second, it is necessary to perform an exhaustive search of cluster potential energy surfaces to ensure that non-intuitive but potentially important structures are identified. Basin-hopping is one method of mapping potential energy landscapes which uses a targeted Monte Carlo with minimization scheme. One begins a random walk across the potential energy surface, conducting geometry optimization at each step to project the current nuclear configuration onto the most closely related local minimum. In doing so, the potential energy surface is transformed into a series of interlocking staircases where plateaus correspond to stationary points on the landscape. Importantly, one can introduce simulation criteria such as defined cluster volume and thermal distribution relative to the lowest energy structure to bias the search towards chemically relevant low-energy species. With a knowledge of the local minima and the transition state energies, a disconnectivity graph can be drawn to visualize the energy landscape. In these diagrams, configuration space is represented by the discrete set of minima, each of which has an associated catchment basin. At a given total energy, the minima can be grouped into basins whose members are mutually accessible at that energy. In constructing these diagrams, basins commonly adopt one of three structures, known as tree diagrams. A palm tree diagram is indicative of fast relaxation to the bottom of the basin. A weeping willow structure is associated with relatively slow relaxation to the basin minimum, with increased likelihood of kinetically trapping higher energy isomers during an annealing process. The banyan tree structure is observed for polymorphic species, which are generally inefficient at locating the minimum energy structure in the catchment basin. I hope that you found this short video to be useful. See you next time.